This section, we will define gates on top of qubits. Remember the quantum circuit? We are in process to create a gate in this section. However, in the bigger picture, just a reminder that we are in process to create a circuit. A circuit consists of qubits, which has gate operations on top of it. Then we create more moments, and then we'll have a circuit created. So there are multiple gates which are supported by Circ out of the box. In order to access the code, which we are going to discuss over here, you would use quantum DIY number 2, understanding gates dot the Python notebook, IPYNB. A gate is an effect that can be applied on a qubit or set of qubits. An operation is a gate applied to a set of qubits. Please note that you can access the number of qubits required by a gate by using circ.gate.num_qubits. We'll see this in this hands-on. This picture is from Wikipedia, which shows that these are some of the gates which are available in Circ. These are not all. These are some of the gates. A few sample example gates. So you have poly X gates, poly Y gates, poly Z, Hadamard gates, phase, C naught, control naught, CX gate, C control CZ gate. So don't worry about the gates at this point in time. You can refer a video on gates, exclusively talking about gates. That is more theoretical in nature, and therefore I want to keep everything hands-on. For your understanding purposes, just think that a gate is a logical operation which is performed on top of a qubit. It's a matrix operation. So in mathematics, it's a matrix operation. These are matrices. Hadamard gate, for example, has 1 upon square root 2 and this matrix. We'll discuss about these gates, as I said, in a separate video in detail. So now we are looking at how many qubits does each of these gates take as input. So I have print qubits required for Hadamard, poly X, poly Y, and so on and so forth. And how do you access gates? Again, this format, circ.gate.numQubits. Circ.gate.numQubits. And if I run this, this is how. You will see that the Hadamard, poly, until the T gate, all of these gates take 1 qubit as an input. Number of qubits is 1. And the NOT gate and the swap gate takes 2 qubits as an input, and the Fredkin and the C swap gate takes 3 qubit as an input. Let's do in this section. I'm going to talk about understanding gates, DIY2. You can access quantum DIY number 2 notebook, Python notebook, in the video description section given below in the Google Drive. So you're going to go open this, then say file, save a copy in the drive. Make sure that you make a copy and then start your hands-on. I highly recommend that you complete the previous DIY number 1 and do the hands-on which was given as part of exercise. Next is, again, make sure you have installed pip install circ in the quiet mode. Again, quiet mode is not necessary, but it's always a good idea. Then I do an import, again creating q underscore c circ.line qubit number 3, created 3 more qubits using the line, very same set of steps which we did in the previous section DIY1. Next, as shown in the theory section, we are going to do these statements. circ.h.num underscore qubits, which gives you the number of qubits required as an input for this gates. As we can see after running this, is that the gate Hadamard, Poly X, Y, Z, S, and T use one qubit as an input for this gate, while CNOT and SWAP uses or needs 2 qubits, while Fredkin and CSWAP need 3 qubits as an input. Next, how do you set up gates? Using Z underscore gate, NOT gate, and H gate, you can just run it and you can just print everything. It's a very simple exercise, but it's very effective. You understand each gates and qubits.